All right, buckle up because today we're diving into some seriously mind-bending stuff. You guys send us some really fascinating stuff about this thing called the photon paradox.
And it really makes you kind of question everything you thought you knew about,
Mhm.
time and space and really reality itself.
It really does. It's like we've built this amazing structure of knowledge, with
Yeah.
physics, but this paradox is kind of like a little tremor shaking the foundation.
Yeah, it doesn't necessarily like break our understanding of physics, but it definitely, exposes some cracks in how we think about the universe.
Right. So before we get to the paradox itself, we need to lay some groundwork. We're dealing with photons here. You know, those tiny little packets of light energy.
Right.
And remember how we can tell if a star or a galaxy is moving away from us? It's all thanks to this thing called redshift.
Redshift, yeah.
Yeah.
It's the stretching of light waves. Makes the
Huh.
light look redder.
Exactly.
And what's really wild is that gravity can actually cause redshift too.
Oh, wait, so gravity can affect light?
Yeah. It's like
Right.
light's trying to fight against gravity's pull and it loses energy and its waves get all stretched out in the process.
So it's like light is getting tired as it tries to escape gravity's grasp.
Exactly.
Like, hold on, how do we know this isn't just some theoretical idea? Is there actual proof that gravity messes with light like this?
Oh, yeah. We have proof. Back in 1960, there was this really cool experiment called the Pound-Rebka experiment. They actually used a tower to measure how light's energy shifted because of Earth's gravity.
A tower? That's a pretty creative way to test gravity's effect on light.
Yeah, he was pretty ingenious. And it was a real game changer because it showed that gravity doesn't just affect massive objects. It plays a role in how light itself behaves.
Okay, so gravity affects light. But what about time? Doesn't Einstein's theory of relativity say that gravity messes with time too?
Absolutely. You're talking about time dilation.
Yeah.
This is where it gets really mind-bending. So basically, time actually runs differently depending on the strength of gravity.
Hold on, so if I were hanging out in some crazy strong gravitational field, time would actually slow down for me.
Exactly. Stronger gravity equals slower time. It's like gravity is stretching and compressing time itself.
Whoa. Okay, but we're not just talking theory here, right? We can actually measure this time dilation thing.
Oh yeah, we can measure it with atomic clocks. You take two identical atomic clocks, put one at a higher altitude where gravity is weaker, and it'll actually tick slightly faster than the one on the ground.
So this isn't just some sci-fi concept. It has real-world implication.
Big time. Think about GPS. It relies on these super precise atomic clocks to give you accurate location data.
Right.
And if we didn't account for time dilation because of Earth's gravity, well, our GPS systems would be totally useless. You'd be navigating to the wrong restaurants and missing all your appointments.
Okay, so we've got photons, redshift, time dilation. I'm starting to see how all these pieces fit together into this paradoxical puzzle. All right, walk me through this photon paradox thought experiment. What is it exactly?
All right, picture this. We've got three identical photons here on Earth. Let's call them photon 1, 2, and 3. Photon 1 just stays put. It's our reference point.
Okay.
Now we launch photon 2 and 3 into space.
So two photons are going on a little cosmic adventure. What happens next?
Here's where it gets interesting. Based on what we know about general relativity, photon 3, let's call it our clock, photons should experience time dilation out in space where gravity is weaker. And since time's moving faster for it, its frequency should increase. It'll have a blue shift. Its light will actually look kind of bluer.
So because time is speeding up for photon 3, its light waves are getting compressed, making it bluer. Okay, I'm following so far.
Good. Now, since photon 2 is identical and it also travels from Earth to space, we'd expect it to have a blue shift too. Everything's making sense, right?
It seems to be.
Yeah.
It's kind of elegant how it all lines up with general relativity, but I have a feeling there's a twist coming. What's the catch?
The catch is this. If we bring photon 3, our clock photon, up to meet photon 2 in space, but we bring it up in a container that's moving slower relative to photon 2, which is just freely zooming through space, something strange happens.
Slower. How can anything be slower than a photon which travels at the speed of light?
Right. It's not about beating the speed of light, but about their relative speeds. So imagine photon 3 is in like a little space capsule, and it's lagging behind photon 2, which is just zipping through space. Now, if we measure photon 2 from the perspective of photon 3 inside its slower moving container, we wouldn't see a blue shift at all. Instead, we'd observe a red shift as if photon 2 is moving away.
Wait, our redshift. But they both traveled from Earth to the same point in space. Why would it look like photon 2 is moving away from photon 3?
That's the paradox. It's as if by simply calling photon 3 a clock and putting it in a slower moving container, we've changed how it interacts with photon 2.
So now it seems like photon 2 and 3 are no longer identical even though they started from the same place and ended up at the same destination. This is where my brain starts to melt a little bit.
And it gets even weirder. Even advanced AI like ChatGPT struggles to make sense of this paradox. It's like we're missing some fundamental piece of the puzzle, something about how measurement and observation affect reality itself.
So the photons are playing tricks on us,
Yeah,
leading us down a path of contradictions.
perhaps. Or maybe they're trying to show us that our current understanding of the universe is incomplete.
Okay, I'm hooked. What happens next in this cosmic detective story? How do we even begin to solve this paradox?
Okay, we're back. And my brain is still kind of buzzing from that photon paradox.
Yeah, it's a tough one.
It really is. It's like the universe is showing us a magic trick. We're trying to figure out how it's done. But if even AI like ChatGPT is stumped, where do we even begin to look for answers?
You know, it's like those classic detective stories.
Yeah.
Where the most obvious clues are actually the ones that are leading you astray. This paradox might be similar. We might be so focused on these things like photons and redshift and time dilation as separate things that we're missing the bigger picture. Okay, I like that. So we're looking at the wrong clues. What's the missing piece of this cosmic puzzle then?
One of the most kind of radical ideas I came across in the research is this idea of an underlying material explanation.
Material explanation. So does that mean like photons are made of some kind of exotic matter that we haven't discovered yet or something?
Not quite. It's not about a new type of matter. It's more like a completely different way of looking at reality itself.
Okay.
Like instead of thinking of space-time as this abstract background where everything happens, what if there's a deeper, more fundamental material reality underlying everything?
Can you give me an analogy to help me wrap my head around this?
Sure. Imagine a fish swimming in the ocean.
Okay.
From the fish's perspective, the water is just the environment. It's the background of its existence. It doesn't perceive the water as like a separate thing.
Right. The water's just there. So are we like the fish then, blind to some fundamental reality that's all around us?
It's a possibility. What if this material reality is kind of like the water for the fish, so fundamental to reality that we just don't even perceive it as separate from the universe itself? This could mean that our current physics, which separates the observer from the observed, is just too limited a perspective.
So you're saying that maybe this photon paradox is popping up because we're trying to separate ourselves, the observers, from the photons, the observed, when in reality it's all part of the same interconnected system.
Exactly. This perspective suggests that photons and these measuring devices aren't really separate entities. They're all just part of this underlying material reality. So the redshift that we observe might not even be like a fundamental property of the photons themselves, but it might just be a result of how this underlying material reality behaves when we try to measure it. It's like the redshift is an emergent property, a consequence of the interaction between the photons and our measuring devices, all within this deeper material context.
So the redshift is real, but our interpretation of it might be off because we're looking at it from a limited perspective. We're back to that fish analogy. Our perception is shaped by the water we're swimming in, this material reality that permeates everything.
Precisely. And from this material perspective, the photon paradox might not even be a paradox at all. It might just be a reflection of our incomplete understanding of how this material reality actually works.
Okay, so it's a humbling thought, isn't it? To think that our entire understanding of the universe could be based on this limited view of reality. But if this material explanation is so radically different from our conventional physics, how could we even test it? Is there any way to peek behind the curtain and see this deeper reality?
Well, that's the really exciting part. This paradox is pushing physicists to think outside the box. They're having to come up with new experiments and new theoretical models that could actually probe the fundamental nature of reality itself.
So they're trying to find ways to see the water, so to speak. So there's hope. Maybe this paradox, perplexing as it is actually the key to unlocking a whole new understanding of the universe.
Think of it as like a cosmic challenge, a puzzle that's forcing us to rethink our most basic assumptions about reality. And who knows, maybe solving this puzzle will lead to discoveries that we can't even imagine yet.
We've been on quite the journey with this photon paradox.
Yeah, we have.
From those photons and redshift to time dilation, and now this mind-blowing idea of an underlying material reality.
Yeah.
It's like we're peeling back the layers of some cosmic onion, and each layer is even more bizarre than the last.
And just like with any good mystery, the closer we get to the truth, the more questions seem to pop up.
Exactly. So let's try to recap this paradox one last time. So we've got these three photons. One stays here on Earth, and the other two go out into space. And based on what we know about general relativity, they should experience a blue shift, because of time dilation. But when we use one of those spacefaring photons as like a clock and bring it up to meet its twin, but we do it in a container that's moving slower, well, then we get a redshift instead.
Right.
It's like those photons aren't even identical anymore, even though they started in the same place and ended up at the same destination.
Yeah, it really does kind of mess with your intuition about how time and space work.
It does.
And then these possible solutions, like that material explanation, well, they really force you to question, like, the very foundation of our understanding of physics.
Right. This material concept is so intriguing. It's like we're just fish swimming around in this ocean of material reality and we don't even know it. Yeah. It's humbling to think that our perception of the universe could be so limited.
Yeah, it is humbling. But, it's also incredibly exciting. It means that there's so much more to discover about the universe and our place in it.
So what are the implications of all this then? If something as fundamental as a photon can lead to such a crazy paradox, what other mysteries might the universe be hiding?
I think it suggests that we've barely even scratched the surface of how the universe actually works.
Right.
And this paradox, as strange as it is, it's a good reminder that the universe is full of surprises.
It makes you wonder, it's like all of our current scientific models are kind of like looking at the universe through a keyhole. We're only catching these tiny glimpses of the big picture.
Perhaps. But the beauty of science is that we're always refining our instruments. We're making that keyhole bigger. We're expanding our understanding.
Yeah.
Paradoxes like this, they're kind of like signposts. They're pointing us towards new avenues of exploration.
So what's the takeaway for our listener then? What should they be thinking about after this deep dive into the photon paradox?
I'd say never stop questioning. Never stop exploring. And never underestimate the power of a good paradox to shake up our understanding of the universe.
Beautifully said. We might not have all the answers, but that's what makes this journey so exciting. The universe is full of mysteries, just waiting for us to unravel them. And who knows, maybe one of our listeners will be the one to finally crack the code of the photon paradox.
Yeah, keep looking up, keep asking questions, and never lose that sense of wonder. The universe is a vast and mysterious place, and it's waiting for us to explore it.
And that brings us to the end of our deep dive into the photon paradox. Thanks for joining us on this mind-bending adventure.